All right, so here is where I actually start talking about the central limit theorem. And in its essence, the central limit theorem states that for any random variable of any distribution, as long as we are looking at a large sample size, when we look at how the sample means compare to one another, they tend to form a normal distribution. They relate to a normal distribution. And this phrase, the sample size is large, is a bit vague on an IB for IB purposes. Generally, it'll be at least 30 samples. And the idea is when you look at more and more sample means, which means you take a collection of data and you find the sample of that collection, and then you repeatedly do that. Over time, if you look at how those means compare, they form a normal distribution or something similar to one when we have enough data. And so to look at this, I have a bit of an vague abstract question here, but I got a sample size of 54 points here from a population that we know has a mean of 41 and a standard deviation of 2. And just keep in mind, if the standard deviation is 2, that means we know the variance here must be 4. Standard deviation squared. And that's what we know about the population. But we're looking at a sample that was taken from this population. So we want to find the probability that the mean of these samples, not the mean of the population, the mean of these samples is between 40.7 and 40.1. Like it says, namely the probability that is between these values. So I'm just repeating myself. So we can't immediately use all the data of the population because we're just looking at a sample of it. However, we can immediately use the mean. In general, the mean of the population we can use as the mean of our data as an approximation. So in this case, it's 41. However, the variance of the sample, our expected variance, will not be the same as the variance of the sample. Sorry, the variance of the sample will not be the same as the variance of the population. And the larger the sample, the smaller our variance is. We saw that before. And so if the population has a variance of 4, we need to divide that by the size of our sample, which is 54. So 2 over 27, which means the standard deviation will be the square root of that, or we call it the standard error we saw last day. Standard deviation, standard error, I'll write error because it's less writing, is the square root of this. So we could write the square root of 2 over 27, or I could write it as, I could square root this, which would be just 2 over the square root of 54, whatever makes you happy. Now, these are the values I'll need for my GDC in a moment, that mean and my standard deviation. And so now I can use my normal CDF, which we started using the last day as well, I believe, in which my lower limit will be 40.7, my upper limit will be 41.3, the mean will be 41, the standard deviation will be this, which again, is not exactly the same as the standard deviation of the population. And we should get a probability to 3 significant figures of about 0.730. And keep in mind, the larger our sample gets, the more and more our variance will shrink. The more and more we'll have means that are closer and closer to the mean of the population, which means the more that this probability here will shrink. It'll get closer to 0 because the larger our sample gets, the more likely it is that our sample mean will get closer and closer and closer to the actual mean. So for this question, it's kind of the other way around. The question is, well, what if this probability was going to equal 0.8 or be more than 0.8, which means at least 80%? How big of a sample would we need to see for that to be the case? And I know it must be more than 54, because when we have 54, a sample size of 54, our probability was close to 80%, not quite. Yet we know the larger the sample, the more likely our values will be closer and closer to the mean. And so, but I just don't know what the value is. So for this, we need to use our GDC to make a graph, but graph our normal cumulative distribution function. And so I'll make a graph of 2 equations. Y1 will be, again, the normal cumulative distribution function with our mean, with our lower limit of 40.7, our upper limit of 41.3, our mean of 41, and our standard deviation being almost the same as this, but this here was for 54 samples. I don't know, I'm trying to solve, so n samples. So it would be, standard deviation would be 2 over the square root of n, or if we're using our graphing calculator, probably an x we would put there. And when you graph that, you will see a graph of all these different possible probabilities depending on the size of the sample. Keep in mind that your x here is the number of samples we're taking, and whereas our y is a probability. So your y-axis will definitely be from 0 to 1. Your x-axis, do a bit of trial and error to figure out the sort of range we want to look at. The other equation I want to graph is just 0.8. And you should see, unfortunately Desmos can't do this nicely for me, or at least I'm not aware of it. You should see one graph that looks something like this, one graph that looks something like this, and they will cross at approximately 73. And so the question does ask, what is the minimum number? So we need at least 73 samples. If you take at least 73 samples of this data, we have an 80% probability that the mean of the sample mean will be between 40.7 and 41.3. And again, the larger the sample, the greater the probability it'll be between there, because more and more it'll approach the actual mean. That's it. The central limit theorem applies to any distribution if we have a large enough samples. And here I have a binomial distribution. And so recall, a binomial distribution has just the number of trials and the probability of success. And so first, let's recall a few things about a normal distribution. If we have, a binomial distribution, the expected value of a binomial distribution is just n times p, the number of trials times the number of the probability of success. So in this case, it's 10 times 0.6, or just 6. So whatever this normal distribution is, there's an expected value of 6. You do this, there's 10 trials, 60% chance of success each time. We would expect there to be 6 successes in those 10 trials. Variance, you may recall, or you probably forgot, is n times p times q, the probability of success. So in this case, 10 times 0.6 times 0.4, in which case we get 2.4. That's the variance of the binomial sample. The idea is, though, we conduct this experiment, we see what the actual value is of how many of our successes, but we do that 35 times. And so since we're doing this many times, if we look at the mean of all these 35 samples, we can expect it to follow something similar to a normal distribution. So now I can say that x will follow a normal distribution in which the mean will be 6. That's what we're going to use. But our variance will not be this. It'll be related to this. It'll be this divided by the number of samples. So our variance would be 2.4 divided by 35. Which means our standard deviation will be the square root of 2.4 over 35 that we're using. And now we can actually answer the question, because we found a way to take this and bring it back to a normal distribution. And again, we're looking at this normal distribution here, even though it's based on a binomial distribution. And so again, I will use the normal cumulative distribution function with the lower value being 6.5, the upper value being some very large number, the mean being our expected value all along, the standard deviation being this, the square root of variance divided by the number of trials. When you do that, you should get a probability of approximately 0.0281. So remember again, the key idea of this central limit theorem is that it does not matter what type of distribution we're looking at. If we take many samples from any distribution and compare the means of those means tend to form themselves a normal distribution. All right, let's bring things to the farm. A peach farmer uses large boxes to deliver his peaches to the market. The farmer's peaches have a mean weight of 175 grams and a standard deviation of 5 grams. Calculate the minimum number of peaches the farmer must put in each box so that in at least 90% of the boxes, the average weight of the peaches is no less than 174 grams. All right, so the idea is we have essentially by putting a number of peaches in, we don't know how many, but that's our sample size. So again, we don't know how many peaches we're putting in. We don't know how many times we're repeating. Each time there has a mean of 175 with a standard deviation of 5, but we're repeatedly doing it. And so this is going to be similar to one of the first worked example. That said, let's get it set up a little more formally. We're going to have a normal distribution with the mean of 175. The standard deviation is going to be the variance. Well, actually, before I get to standard deviation, let's do the variance. The variance will be 25 divided by the number of samples, the number of peaches in this case. We don't know what it is, so I'll put an n, which means the standard deviation or the standard error will be the square root of 25 over n, or just 5 over root n. And that's what we'll need in a bit. And so now, again, I need to use my GDC to show different possible values for n and how they relate. And so one of the equations I'm going to graph is the normal cumulative distribution function with, again, the minimum being 174, maximum being a big number, the mean being 175, the standard deviation being 5 divided by the square root of x. My other equation is, well, in this case, I want there to be at least 90% of the boxes fulfilling this. And so that means I want my other equation just to be y equals 0.9. And again, we'll see something quite similar to before. One curve looking like this, one being a horizontal line. And they should cross at about 41.059, so a little bit more than 41 boxes. And since we have to have a whole number of boxes, we must bring it up to 42. So there must be a minimum of 42 boxes to ensure that at least 90% of those, 90, not boxes, 42 peaches, poor peaches. There we go. And if we have a minimum of 42 peaches in each box, then we can rest assured that 90% of them will have an average weight of the peaches no less than 174 grams. A lot of stuff to think about here. There's lots of ways we can approach this. And so, yeah, don't be surprised if this is one of the more challenging parts.